Now we get down to ARIMA, and we have covered ARIMA in details. When we look at the theoretical backgrounds of the different forecasting techniques, so we have a fair amount of knowledge about ARIMA by now. We know what it is. So ARIMA is, if you recall, it's autoregressive, integrated, moving averages, has three parts. AR part stands for the autoregressive, where we regress the data on itself. We estimate the current value of the data from the past data points. Integrated because we need to difference the time series, and we are going to recap those quickly once more. Integrated because we need to make the time series stationary by differencing. Moving averages is that we take a linear combination of the errors over time, starting from the current value to as far as we want to go back, to estimate the current data point. So first we auto-regress, and then we take the linear combination of the error terms to estimate the data as well. Now, why ARIMA? Like, we haven't quite touched on this topic in our background. The thing is, ARIMA is in effect like we are using the error terms. So in effect, it is leveraging the autocorrelations between the data points. That is how correlated the data is between one time point and the time point before. So there are some thoughts, but do not read too much into it. There are some thoughts that ARIMA is perhaps supposed to perform better than exponential smoothing. Well, the other difference is in exponential smoothing, we do not need the data to be stationary, though that's not quite true. But for ARIMA, it is essential that the data be stationary. And we'll touch on those points again as we move along this lesson. But the main thing is ARIMA uses the autocorrelation, so perhaps it might be a little more robust than exponential smoothing. But there are thoughts both for and against this belief, so I just wanted to point it out, but do not read too much into it, and see what the steps in ARIMA are. So you have this, you start out with this time series, and as we have already discussed, for ARIMA it's essential that the time series be stationary. So first you need to make the time series stationary by differencing, and we'll see how to difference in R. Once we have a stationary time series, you build and select a candidate ARIMA model, and which basically is referring to the PDQ parameters of ARIMA or the orders of ARIMA. So the P refers to the autoregression part, the D is the differencing part, and the Q is the moving average part. So we need to decide like how far back in time we'll go to add the terms to the autoregression and the moving average equations. And also the D part is related to differencing, so we need to decide how far we need to difference, how many times we need to difference to make the time series stationary. And once we have this candidate ARIMA chosen, we can use that candidate ARIMA to make a forecast. So these are basically the steps in ARIMA. Now, quickly revisiting the topic of stationary, why do we need time series to be stationary? So that the past patterns are replicated in the future. And by a stationary time series, statistically speaking, it means that the time series has constant mean and variance over time. Perfect example of such a series is pure white noise. We have looked at pure white noise before. Basically, the fluctuations of a pure white noise, the random fluctuations, are evenly spread across time. It has a mean of 0. The distribution is totally random. So we can confidently say that pure white noise has the same patterns in the past as in the future. And if that is how it is, then we can make a forecast easily based on the past data. Of course, we'll never find a real life time series which is totally like pure white noise, and that is why we'll need to difference it to make it stationary. And what was differencing? Differencing was taking the differences between successive data points. So it's the difference between yt minus 1 and yt, or yt minus 2 and yt minus 1. And if you recall, like we used the example of distance, velocity, and acceleration. Velocity is stabler than distance, and acceleration is stabler than velocity. Velocity is the rate of change of distance, acceleration is the rate of change of velocity. So what I'm trying to say is that the rates of changes or the differences are usually more consistent than the data itself. So when we take the difference between yt minus 1 and yt, these differences are more consistent across time than the y's per se. So if we difference once and see it's still not consistent, we need to difference once more and keep going till we find that the pattern looks totally consistent or stable across time. Now this is the data we are going to use, and this again is available in Rob Hindman's website. We are going to use the age of death of successive kings of England. This time series is what we are going to use to step through ARIMA. So first thing first, here on the right bottom I have the pure white noise, and on the top left I have the actual data. So first thing first, whenever you get a time series, you plot it. And when you plot it, let's do one thing at a time. Let's first compare this actual data with pure white noise. Does this data look like pure white noise? No. I mean, this is no way consistently random. It is like falling too much over here, it's rising too much over here, plus, I mean, it's definitely not consistent across time. That's very easy to say. So now we've got to make it consistent across time. That is, we need to make it stationary. The way we do it is using the diff function that we feed in our raw time series into the diff function. And mind you, like before I proceed, just want to remind you, like even before you do this, you need to read in the data, you need to convert it into time series using TS, and as we have seen, the first thing I'm assuming you already know to do is to plot the time series. You have to plot the time series in case of ARIMA to check if it's looking like pure white noise or not. If it doesn't, well, you need to difference it. So you start differencing using the diff function, and you tell it this differences option. Via this differences option, you tell the function to difference it once. If this is 1, it's going to take the first differences, that is just the yt minus 1 minus yt, or yt minus 2 minus yt minus 1. So it's going to take differences just once. We store the differences in this diff vector, diff1 vector, because we are differencing just once, and then we just plot the differences. Now this right bottom again has the original raw time series. Compare this actual time series with the differenced one. This is the differenced one. Have a quick look at the pure white noise again. So if you look at the differenced time series, that is this guy, this is definitely more random compared to this. This is more consistently fluctuating across time. That is one way to say if your data looks more stationary. That is by plotting it. You plot it and see if it's looking more evenly spread out. The other more objective way of doing it is to use a formal test for stationarity, and these tests are known as unit tests. One type of unit test is an ADF test, that is an augmented Dickey-Fuller test. Now if you perform an ADF unit root test on pure white noise, it gives you a test statistic of minus 12 with a p-value of 0.01. So 0.01 is below 0.05. So this test statistic is definitely significant. And this is going to be kind of our reference to know if our data has become stationary enough. So what are we going to do? We are going to take the original time series, perform an ADF test, and all you need to do is feed in your original time series to the ADF.test function in R, and it's going to spit out the Dickey-Fuller test statistic and the p-value. So here you can see that first thing to note would be that the p-value is 0.32, that is above 0.05. So this test statistic is not significant. Next, you do the ADF test on the difference time series and look at the p-value first. The p-value is 0.01, so this test statistic is significant. Next, compare the test statistic of the difference time series with the original time series. This test statistic is more negative, that is, this is smaller compared to the original one. And what is the ideal decay-fluid test statistic for a perfectly stationary series? For a perfect stationary series like pure white noise, the test statistic is minus 12. So if our difference series shows a lower value than the original series, we are going to conclude that our time series has been differenced enough, that is, it is sufficiently stationary. And to test it, what you can do is you can difference it once more, that is, you can use differences equal to 2 and compare the ADF test statistic of difference 1 and difference 2, and if difference 2 does not show a smaller test statistic, then you can be confident that this has been differenced enough. Don't over difference your series at the same time. So just optimally difference it. So that's the way to do it. Like first, to sum it up, first you plot the difference series, see if it's looking more random compared to the original series. Next, you perform the ADF test and you keep performing the ADF test till you get a stationary series. So you keep performing your ADF test till the time the test statistic does not become lower any longer. So in our case, I did difference a couple of lines and saw that it's good enough to go up to differences of 1. And this test statistic is lower than the original, it's more significant, so we can be confident that the first difference series is stationary enough. So now we have got one of the orders of ARIMA. We now know D. D, if you remember, like D refers to the number of times we difference. We have difference just once, so D is 1. We still need to figure out P and Q. So how to figure out P and Q? Well, in the background section, we discussed about the ACAF, that is the autocorrelation, and the partial autocorrelation plots. And those are the plots that are going to help us select the candidate ARIMA model. That's going to help us decide on the values of P and Q. So now here, again, what we need to look at the spikes. We'll ignore the spike at lag 0. So we have plotted we are now using one thing to note is that going forward, we are going to use the difference series. We are no more going to use the original series while selecting the candidate ARIMA model. So we use the difference series, fit that into the ACF function. You are now super familiar with the ACF function, and ask the ACF function to plot the autocorrelations up to a lag of 20. And what we need to look at the spikes, that is the plots that are exceeding the boundaries of significance levels, these blue lines. So now we always ignore, even if there's a spike at lag 0, we ignore that. We start by looking at the successive spikes, and here we see that we have a spike at lag 1. And what are we going to conclude about that? So the spike at lag 1 exceeds the significance bounds, like its value perhaps, like the autocorrelation value perhaps is like minus 0.360. And one more point that I repeatedly mentioned before as well, it doesn't matter if it's spiking above or below, that whether it's exceeding, going past the blue line above or below doesn't matter, the sign doesn't matter. So here it's spiking below and its value is like minus 0.36. So beyond lag 1, the autocorrelations decline, and that helps us to decide Also, like, let's quickly have a look at the actual values of the autocorrelations. Again, we use the different series, we plot, or rather we go up to 20 lags, but we don't want the plot, so we set plot equal to false in the ACF function, and that will make ACF function print out the actual values of autocorrelation. So on the top of both the rows are the lags, that is 0, 1, 2, 3, 4, etc., up to 20, and at the bottom are the actual values of the autocorrelation. So we see that beyond lag 1 has an autocorrelation value of minus 0.36, but beyond it, the autocorrelations actually go down and down and down. So that is the cutoff. That cutoff helps us decide the Q value. Remember that autocorrelation relates to the moving average part, the order of the moving average part. So it tells us that the order of the moving average part is 1 because it spiked at 1 and then declined. And that theoretically means that we are going to take just one of the error terms, that is ET minus 1, into consideration in the moving average part to estimate a current data. Anyway, not to worry too much about the theoretical background, but practically this tells us that Q is 1. Let's move on. Next we need to plot the partial autocorrelations. Again, we take the different series, plot the partial autocorrelations up to 20. And here again, like the first one, the first spike, we do see spikes, right? These three plots are going past the blue line. It's all negative in our example, but it might also have been on top. But a spike is a spike. As long as it goes past the blue line, it's a spike. So the first one corresponds to lag 0. It's 1, 2, 3. Let's say this is 1, 2, 3. So here's the cutoff spike, like beyond which there are no more spikes, but the PACF kind of exponentially declines to 0, goes down to 0. So the last spike in the row is for lag 3. So this gives us the P value. Again, you can set plot equal to false in the PACF function and actually look at the partial autocorrelation numbers. And here you clearly see that beyond lag 3, the numbers are all declining and declining pretty much to 0. So 3 gives us the value of P, that is the order of autoregression. So we are going to take 3 lag terms of the actual data to estimate our current data. So YT will be estimated on the basis of YT minus 1 and YT minus 2 and YT minus 3. And for the moving average part, it's going to be an order of 1. So this sums up what we have inferred from our autocorrelation and partial autocorrelation plots. The correlogram, or the plot of the autocorrelation, is 0 after lag 1, and the partial autocorrelations are 0 after lag 3. So 1 and 3 are the cutoffs. And moving on, we see that our ARIMA, now if we forget about the I part, we already know the I part. So if we leave the I part, we call the model ARMA, that is just autoregressive and moving average. We are forgetting about the integrated part. We see it can either be 3 and 0. 3 comes from the partial autocorrelation plot. The cutoff spike was at 3, so it can either be 3 and 0 or 0 and 1. So 3 gives us the order of the autoregression part. So either we can take a model in which we'll autoregress 3 terms and keep the moving average at 0, or we can, the autocorrelation cutoff of 1 gives us the Q, that is the order of the moving average part. So we can otherwise take an autoregression of 0 terms and a moving average of 1 term. So these are the two potentials. That is how we are going to do it. So now we have to decide which one shall we choose. And we are going to use what we call the principle of parsimony. So that is, we are going to add up P and Q and see which gives us the smallest number. So 3 plus 0 is 3, 0 plus 1 is 1. So this guy actually gives us the minimum of the sum of P and Q, and hence we are going to choose an ARMA model of 0 and 1. Okay, is this part clear? So we first get the P and Qs. The P is something we get from the partial autocorrelation plot, and the Q is something we get from the autocorrelation plots. Partial autocorrelation gives us the order of autoregression. So it's P, we decide between the cutoff value for P and a zero value for moving average in this case, and then we decide between zero order autoregression and first order moving average. We use the principle of parsimony and see which gives us the least order or sum of orders, and since in our case the least sum of orders is 1, we choose the ARMA 01 model. And hence our ARIMA, we already decided on the D. We know that in our example we just need to difference ones. So our final ARIMA model will be 0, 1, 1, and that's what we are going to use to build a model. So now we get back to our original time series. Our original time series is the King time series. We use the original data. We use the function ARIMA and tell it that we need an order of 0, 1, 1, and ARIMA gives us a model which we store in the King time series ARIMA vector. We print out the King time series vector, and these are the parameters it prints out. So this is the coefficient that the model is going to use to build future forecasts. Now we are going to actually forecast outside or beyond our actual data. So we use the forecast function again that we use for Holt winters, but this time we tell the forecast function that we are doing ARIMA, so it's forecast.ARIMA. We feed it in the model vector, the forecast time series ARIMA vector. Tell the forecast function we want forecasts for 5 more periods, and here I actually show how to tell the forecast function to give us forecasts at a 80% confidence level. And if you have fed all those parameters to the forecast function, it does the out of time forecast, and this is how the out of time forecast looks like. So here you see that we are using an 80% confidence level. The second column gives us the averages of these two extreme, the lower and the upper bounds of the forecasts, and plus we have these lower and upper bounds at 80% confidence level. So next thing is to validate, and we plot the forecasts. This plot function along with the plot.forecast function rather gives us the actual data plus the forecast. The blue line is the forecast, the black plot is the actual data. And we do see that the blue line is pretty much in the same ballpark of the most recent actual data. The orange part is again the 80% confidence level, and the yellow part the 95% confidence level. But we have chosen just to use the 80%, so no need to worry about the rest. But the key bottom line from this plot is the forecasted values are pretty close or in the same ballpark of the original or actual data. So we are doing good. Next, if you remember, like while discussing the ways to select the ARIMA model, like in a background section, we discussed about the autocorrelation and partial autocorrelation plots. And as we have already done right now, that we have used the ACF and the PACFs to decide the P and the Q orders of ARIMA. But that said, I definitely mentioned before that that's not good enough. Like even after building the model and forecasting, we should look at the autocorrelations of the residuals. Even the residuals should not be autocorrelated, but they should be randomly distributed. And that is why in this step, like after you have done your forecasts, take the residuals are available in the residuals variable of the vector in which you stored your forecasts. And this is something we are already familiar with from our Holt winters walkthrough. And we plot the autocorrelations for 20 lag periods. And what do we see? We're never going to consider the spike at lag 0, right? So if we leave that one out, we see that none of the autocorrelation plots go beyond the blue line, neither above nor below. So we are good. Our residuals are not autocorrelated. Next step, if you remember, for Holt-Winters, we want to objectively, statistically conclude that our residuals are not autocorrelated, and we perform the box test. We feed the box test the residuals from the residual variable and for all the 20 lags, and then we look at the p-value. The p-value is above 0.05. So the box test statistic is not significant. We can conclude very well that our residuals are not correlated significant. Last but not the least, this is the same stuff that we did in Holt-Winters. Like once we have forecasted, we play around with the residuals, we look at the autocorrelations, we do the box test, and last thing, if you recall from Holt-Winters, what we need to do is to see if the residuals are truly randomly distributed. So we plot out the residuals. We plot the residuals, and here, as you can see, it is definitely randomly distributed. If you draw a line from this 0 on the y-axis and draw it across the plot, they're kind of same number of data points or residuals above and below that 0 mean line. So we can conclude the mean of the residuals is 0. So the residuals basically average out and they are randomly distributed. And last but not the least, we need to be totally convinced about the fact that the residuals are random, and we plot the histogram. We have this bell-shaped normal distribution curve, the blue curve overlaid on it, and this histogram tells us that the mean is of the residuals is 0 and there are equal number of residuals on either side of the mean. So that again tells us the same thing, that the residuals are both the positives and the negative residuals, error terms cancel each other out, and that if we take the average of the residuals, it's 0. So overall there is no significant error in our forecasting. So that kind of wraps up our elaborate way of doing ARIMA. And what are the things we did? Going through it real quickly, like we first took the data and plotted it. That's the first thing that you always need to do with time series. Compared it against white noise, that is pure stationary series. We saw our data is not perfectly stationary, so we differenced it. We differenced it once, but in real life, when you are dealing with other time series, you might do difference multiple times. And you tell the diff function how many times to difference using the differences option. So you can use either 2, 3, 4, etc., whatever you want. However, in our example, we differenced it just once and we plotted the difference series, compare it with the original series, and we see that a difference series is more random, consistently more random across time. So it is sufficiently stationary. That's the visual way of saying that our data has been sufficiently differenced. Next, we perform the ADF unit root test, and pure white noise, which is perfectly stationary, has a ADF test statistic of -12 with a p-value of 0.01. So it has a significant, perfectly significant statistic value of -12. So we compare our ADF test statistic of the difference series with the original series, and we see that the difference series has a p-value of 0.01. that is a significant p-value, and the decay test statistic is lower than that of the original series. So if it's lower and cannot get any lower, then this is the optimal differencing point. We do not need to difference any further. So you need to just difference once more and see if it is getting any lower. If it doesn't, we should stop here. Don't over difference it as well. So the differencing part is done. So out of the P, D and Q that we need to decide about around the orders of ARIMA, we already know D. Then we have to decide about P and Q. To decide about Q, we plot the autocorrelations. We look at the cutoff spike. We see that the cutoff spike is at lag 1. Beyond that, the spikes are not, it doesn't spike. the autocorrelations are not significant. That is, it is neither above or below the blue lines at the top and the bottom. So we decide that our Q value is 1. We can also print out the autocorrelation values to know which lag will help us determine the Q value. Here we see it's 1. Next, we plot the PSEF, the partial autocorrelation, to determine the P value, that is the order of autoregression. And in either case, both for the ACF and the PSEF, we use the difference series. That's a point to be noted. From a PSEF plot, we see that the lag 3 is the cutoff spike. Beyond that, all the PSEFs slowly or exponentially decline to 0. We can also print out the PSEF values to be sure that we are choosing the correct P value. And once we have chosen the P and the Q, we use the principle of parsimony, that is, we sum up the P and Q to see which gives us the least sum of P and Q. So in our example, P plus Q is smallest in this case, in this scenario, when Q is 1. So we choose an ARMA model of 0, 1. We already know the I part, that is 1 in our example. And hence we decide that our ARIMA model has the orders 0, 1, 1. We use those orders to tell the ARIMA function to build the model using the original time series, not the difference time series, but the original time series. And then we start validating. We do our forecast first, of course, and then we start validating. We plot the forecast, see if it is in the ballpark of the most recent actual data. We plot the autocorrelations of the residuals and see if they spike at all. In our example, the autocorrelations do not spike. We perform the box test to see if the box test statistic is significant or not. In our case, it's not significant. Hence, we can conclude the residuals are not significantly autocorrelated. Then we plot the residuals to see if they are randomly distributed or rather normally distributed with a mean of 0 and constant variance. Finally, we plot the histogram to prove the same point, and in our example we see that our error terms or the residuals do have an average of 0 and they're equally distributed on either side of the mean. So our residuals definitely overall cancel out and there's not much significant error in our forecasting. So that wraps up the longer way to do ARIMA, and that is kind of the more traditional way. But again, like we had the ETS function to do our exponential smoothing, we have a shortcut ARIMA procedure, and in that procedure you do not need to go to such elaborate extent to determine your P and Q. So if you use the function auto ARIMA, this is an automated ARIMA process. So what you need to do is you just need to provide your original data set. So you read in your data, you convert it into a time series data and feed auto ARIMA your original time series. The moment you do it, auto ARIMA spits out the order of the ARIMA. So it tells you that your ARIMA should be ARIMA 300. And that is what you use then in your ARIMA function to build the model. You tell the ARIMA function that your order is 300 and that builds the model. Then you can use the model that you have built to do your forecast. And this is an example that I've taken from something I worked on. But basically once you forecast, you get the point forecasts and the highs and lows. It's same as before. And that basically concludes our discussion of ARIMA. So in auto ARIMA, the only difference is you do not need to use the ACF and PACF plots to determine your P and Q. All you need to do is take the original data, or rather just difference it, then take the differences of the original data and feed it into auto ARIMA. It will tell you the orders, and once you have the orders, you build the model using the ARIMA function and feed in the orders that you have got from auto ARIMA. and then you can forecast using the forecast function. So here's a quick highlight as to why you would want to use these two automatic forecasting functions that we have talked about, that is the ETS function and the auto variable. First thing first, of course, you've got a sense that it's pretty complicated at selecting the right model using the elaborate procedures. So not everyone is an expert at choosing the right model, and during a discussion of the ACF and PACF plots, I did mention that those plots are not always very clean, so it's not very easy to use them to select your right model. Next, you may be required at your job to build thousands of forecasts within a very short time, so you don't want to waste time to interactively build the model. And next, lastly, you might need to use number of time series, separate time series data to to integrate together and forecast your original time series. So in that case also you want to move quickly and you want to perhaps prefer to use the automatic functions. So that wraps up our hands-on or training of forecasting with time series. The last small piece is about validation, and I'll quickly wrap it up in the next section.